In the last video, we implemented the simple example of solving the heat equation PDE in FEniCS using simple 50 lines of code, including the selection of a function space, the implementation of the weak form, as well as the interactive simulation loop, including a plotting. In this video, I want to go over all the steps in more detail. We're going to derive the weak form and demystify many of the statements of the script. Let's get started. Hi and welcome to this new video. The 1D diffusion equation is probably one of the most simple partial differential equations you can solve, and here we're going to use the finite element method to simulate it using FEniCS and Python. For this, I first want to quickly recap on what the partial differential equation looks like, or in more precise terms, we're looking at a so-called initial boundary value problem, and this IBVP consists of first the partial differential equation, and the heat PDE is given as the temporal derivative of a quantity. You can, for instance, think of it as the temperature in a one-dimensional rod is equal to the second derivative of that quantity with respect to x. And of course, we have a partial differential equation because we have derivatives with respect to not only one quantity, but here we have it with respect to t, the time, as well as x, the space. And then there is a constitutive parameter, alpha. You can kind of think it as the temperature diffusivity, or in other words, how fast temperature is moving through our one-dimensional rod. And then we have to define our PDE on a domain, and x is given in a domain, usually that's called omega, and this domain shall be the unit interval, so the interval from 0 to 1. And then this PDE is valid for t being greater than 0. So this one here is our PDE, our partial differential equation. That's basically the model that we use in order to describe diffusion. Then we need an initial condition, so we need to know what the state was in the beginning of our simulation. So we will say u at t being 0 and x is going to be given according to an initial condition, and here, in accordance to the previous video, we will choose the sine of pi times x. We will look at it in a second, and this is basically just a small arc on our domain, where we have a peak of temperature in the center and 0 at both ends. And then this, of course, is valid on the entire domain omega, which was this unit interval from 0 to 1, and it is valid at time being 0. I mean, we've already written that down here. So this one is the initial condition, so the initial condition, or IC, and then we have a boundary condition, and for this we will use u at all times t, and x being 0 is going to be 0, and I will just also use that on the right end, so u at t and x being 1. And this is valid, well, on the boundary points, so I don't have to explicitly say that here again, but it is valid for all times greater than 0. And in essence, these are homogeneous Dirichlet boundary conditions, so let us also note that down. This is an homogeneous Dirichlet boundary condition. And you will see this initial boundary value problem appear multiple times when we then implement it and also look at the discretization. Okay, let's look at the initial condition for a second. So let me just say initial condition, and our domain is going to be the interval from 0 to 1 on x. And then we basically have another axis. Let's, for instance, draw it here. And this is our u, the temperature. And then at time equals 0, we will be having an initial condition according to this arc. And if you were to continue it, this would be like a sine function, and we're just taking the first arc of it. And it's of course 0 at both ends. So this is sine of pi x, and that's the initial condition. And the property of the diffusion equation is that we are diffusing out this profile. And since we will be having homogeneous Dirichlet boundary condition, in the long term, we expect a behavior which is kind of moving our shape downwards. So with increasing time, we will keep the qualitative behavior, but it will get smaller and smaller and smaller, and in the limit it will be just a 0 temperature profile. And that of course makes sense, because if we have homogeneous Dirichlet boundary conditions at both ends, our energy is kind of flowing over the boundary, and then in the long term we will reach this steady state where everything is just 0. That's what we want to solve with the help of FEniCS. But how does this work? First, let us look at the finite element method more conceptually. And the idea of the finite element method is to subdivide our domain using finite elements. So FEM subdivides the domain, and the domain, this was omega. So in essence, this unit interval, this one here, was omega, into finite elements. And finite elements in this one-dimensional scenario just means we have smaller intervals in which our domain is subdivided. So you could think of it in the following way. So let's say we have x, and then it goes from 0 to 1, our omega, and then in there be, for instance, subdivided here into smaller subdomains basically. This one here is one finite element, and here we have basically chosen 1, 2, 3, 4, 5 finite elements in order to make up our domain from 0 to 1. And then going further, we will outfit each finite element with a shape or an Ansatz function, so to say that each element will be given or will be outfitted with a shape slash Ansatz function. And in the simplest case, and that's also the case we're going to look at here, is we kind of take our domain and then we will have two functions on it. We have one linear function which goes like this, and it is 0 on the left end. So this here it is 0, and it is a 1 on this right end. And then we have another Ansatz function or shape function which is going to look something like this, and so they cross in the center, you could say, and this one is going to be 1 on the left end and 0 on the right end. And the crucial point here is that we have nodal values, so we're going to have values that define these nodes here, and I probably have drawn this a little bit terribly. Let me try to draw it once again such that those two Ansatz functions are on the same height. So because they are both 1 here, so we are going to scale them by the nodal values. So these are scaled by nodal values, and in essence the FEM will be the task to find the scalings of these nodal values. And in the end, when we then have an Ansatz function or a shape function in each of the finite element, the superposition of the shape function inside the finite element and then stitching together the solutions again will give us an approximative solution to our partial differential equation. So we can say that the superposition of our Ansatz or shape functions is going to be the solution in a domain. So the superposition is the solution in the domain. And we can also visualize this, or at least I can attempt to. So let's again have our domain. Let's have it from 0 to 1. And for this, I first want to draw a hypothetical true or analytic solution. And of course, we know that at each point in time, we will still have this arc shape. It will just be smaller or larger in the magnitude, depending on the time point we're at the moment. And then this one kind of looks like this. So this one shall be the hypothetical analytical solution. And I mean, here in this one-dimensional heat PDE example, we could actually find the analytical solution, but let's just say for the sake of solving PDEs in more general terms, this analytical solution is of course not available. And then let's subdivide our domain again into our 5 finite elements. So 1, 2, 3, 4, then we have 1, 2, 3, 4, 5 elements. And then in a sense, the task of the finite element method is to find the nodal values to each of the scales of our Ansatz functions. So here in this particular case, those match with the ends of the finite element. And in the best case, they should be on the analytical solution. Let's assume they are. So here we will find a node which is on this particular point. Then we will find a node that is here, and here, and here, and here, and here. And then let's draw the Ansatz functions in each of the domain. So here we will have first the orange one. So maybe I should have used a different color, but here we will have the orange one. And then the purple one will be just a horizontal line. Then in the next domain, there we will have, or the next finite element, we're going to have this Ansatz function, or at least it's going to be scaled like this. And then we will have for the other one, it's going to look like this. And then let's go on. Here we have it in that way. And then this one, and I think you get the pattern. So here it is always like our first Ansatz function, or the first of our two Ansatz functions on the finite element is always 0 at the left end, and then it's going to be the particular nodal value that we found on the other end. And finally we need this one as well. And then we have a 0 one here and another one that looks like this. And now we have to find the superposition. So we will take one element. So let's, for instance, use or check this element here. And then at each point on this finite element, we take the superposition of the two solutions. So we take this one and add it up. Then we are approximately here. I mean, I think you get the point. In the end, the superposition will be a straight line. So we will have straight lines here, here, and here. And approximately this should then resemble our parabola. Of course, these are just a couple of straight lines, so they are not as perfect, but at least there's something. And of course, the more nodes we would use hypothetically, the better our approximation would be. And of course, the way I presented it to you with the finite element just having these two linear Ansatz functions is one of probably hundreds ways of choosing finite elements. I mean, arguably, it's probably one of the simplest. And these form of finite elements are called Lagrange elements. So they are Lagrangian elements, Lagrange elements. And here they are of order 1. And order 1 refers to linear Ansatz functions. And these particular shape of elements, they define the function space. So those define the function space. And in essence, this is what FEniCS will then accept. So FEniCS knows a lot of function spaces and the corresponding ansatz and shapes functions. And so we just have to choose one here. And for the sake of simplicity, and since we have such a well-behaved partial differential equation, let's go for the simplest. Okay, let's start coding what we have so far. So I'm again in the same file as you might have seen in the previous video with just some docstring in the beginning. Then we import a FEniCS package as well as matplotlib. And then we have our main function. I first want to start by defining the number of elements we're going to use. So these are 32. It's a good start. And then we can use this number of elements in order to define our mesh. And since we are in this one-dimensional case, remember, we are just subdividing our interval from 0 to 1 into smaller intervals, and these are our finite elements. And the easiest way of doing so is giving each interval the same length. And this is called a unit interval mesh in FEniCS. And we will create it by saying mesh is going to be equal to fe.unitIntervalMesh, and then the number of elements. These number of elements, as well as the mesh, are going to be used by FEniCS in order to define our function space. And as said, we will use a Lagrange function space of first order for these linear shape functions that we have. So we will be having Lagrange polynomial space first order, and I just want to be really verbose here. And so we're going to say Fe, and then using function space, since FEniCS directly translates from finite element speech into Python in that sense. And this takes a couple of arguments. So first we need a mesh, because of course the mesh kind of defines where these node values will be that are scaled with finite element method. In our simple linear Ansatz function case, these nodal values are exactly on the mesh vertices, but those could also be inside the interval depending on the shape function you choose. And then we will use Lagrange, because we have a Lagrangian space, and then we'll just set the order to 1. So read again, this takes the mesh, which defines the position of the mesh vertices, And then it uses a function space, here Lagrangian function space of first order, and then it determines which are these nodal values that we're going to be solving for later on when we actually solve the FE problem. So this is kind of the setup. Then we also have to translate our initial and boundary condition. So this will be initial and boundary condition that we're going to apply. Let's start with the initial condition. And for this, we of course need to translate this sine of pi x somehow onto our mesh, or more precisely onto the nodal values of our function space on this mesh. And for this, we will first create an expression. Let me call this the initial condition expression. And an expression is just a way in FEniCS in order to represent a mathematical function. And since FEniCS is a tool that kind of lives both in Python and also in C++, you see those two things kind of used interchangeably. Here we want to define this initial condition by the help of a C++ string. So we will say fe.expression and then apply this to the CPP code. You also see that here in the documentation highlighted, which is going to be sine. So this is a standard function that FEniCS or C++ will understand. And then we need pi. I just want to hard code this here to 3.141. And then we need to multiply it with x. But in more general terms, FEniCS is meant for solving PDEs in higher dimensions, not just in one dimension. So we will use index 0, which refers to x0, so the 0th spatial axis, because we have a 0-based indexing. And then we have to set its degree to 1. This is just a hint for FEniCS in how it should be interpreting this expression with respect to our function space. And then we can discretize this initial condition onto our Lagrangian space. So we will do u as the initial condition, and I want to use fe.interpolate, and that's because it just is going to evaluate this function at the corresponding nodes, and then we kind of move it from this continuous world into the discrete world. So let's use our initial condition expression, so initial condition expression, and then the Lagrange polynomial space first order. And I want to call this uold, and we will see later why. That's because we have this iterative time stepping procedure, and this will be the solution from the previous time step for the 0th temporal iteration. Okay, that's the initial condition. Let's translate our boundary condition. So let's create the boundary condition. And for this, we will use FEniCS.Dirichlet boundary condition, because we have a Dirichlet boundary condition. And this one takes 3 arguments. First, we give it the function space, because of course also the boundary condition has to be aware of this function space. Then we need to define the value on the boundary, and this one shall be FEniCS.constant 0, because we want to have our homogeneous Dirichlet boundary condition. Maybe let's be verbose and call it the homogeneous Dirichlet boundary condition. And then FEniCS also needs a function in order to determine whether we are on the boundary or not. Might seem a little bit confusing at first, but it's really easily done. So we will create a function that's called, I want to call it maybe boundary Boolean function. And that takes 2 arguments, first an x and then an on boundary Boolean. And this basically allows us to distinguish between different boundary conditions that we could potentially encounter in PDE simulations. So FEniCS is going to query this function at certain points when it has to determine whether a node lies on the boundary. And it will thereby provide the position it wants to query for. So this could, for instance, be x equals 0.0. And then it is also going to provide us with a Boolean where it says, well, this point is on the boundary, and here is the position on the boundary, please tell us what kind of boundary it is. And since we only have one type of boundary, which is an homogeneous Dirichlet boundary, we will just return on boundary. So this function is called with a position and a Boolean, and whenever the Boolean is true, we are on the boundary. And then we should return whether we are on a certain type of boundary, but we only want to use it with the Dirichlet boundary condition, so we're just going to return the Boolean again. So let's have this one as the next argument to our Dirichlet boundary condition. Okay, with the previous code session, we looked at the mesh, which kind of gives rise to the finite elements. And then we also looked at the initial condition as well as our homogeneous Dirichlet boundary condition. So what we are essentially left with is the PDE problem itself, and we kind of have to hand over this problem to FEniCS. But FEniCS does not understand this particular form of the PDE, which is called the strong form, but it requires us to provide it in the weak form. And as the next step, I want to derive this weak form with you. So for this, let us quickly recap on that. So for FEniCS, we need the weak form, and the weak form is just a mathematical construct which has the characteristics of the strong form, so what you see in the PDE, but technically speaking has less stringent requirements on the differentiability. But for us here, we just view it as a tool, and I will show you an step-by-step algorithm in order to obtain the weak form. So let's turn the strong form into the weak form. So that's what we're going to do here, strong form to weak form. Just for a second, quickly recap the strong form. So the strong form was temporal derivative of u with respect to t is equal to alpha times second derivative of u with respect to x. Well, then our first step is to multiply with a so-called test function. So multiply with test function. So we take our PDE and multiply with this test function. Let's call it v, and it is from a special function space. And we will choose it from the same function space that we defined earlier with these Lagrange polynomials on the small finite elements. And then basically we get du by dt times v is equal to alpha times second derivative of u with respect to x times v. The next step is to integrate over the domain. So integrate over domain. Okay, so we will take our multiplied strong form and perform the integral from 0 to 1 over first left hand side du with respect to t times v dx shall be equal to the integral from 0 to 1 over alpha times second derivative of u with respect to x times v dx. Then we're going to apply integration by parts. So apply integration by parts, and our goal is to move one derivative from u over to our test function v. So we're going to keep the integral on the left hand side. So integral from 0 to 1 du by dt v dx is equal to, well then let's perform the integration by parts. We first get a boundary evaluation of alpha du by dx. So we integrate it once and then multiply with the other function as is, and then evaluate that at x equals 0 and x equals 1. And then we subtract the integral from 0 to 1, and we have an alpha du by dx. And then let's apply, so this is the rules of integration by parts, apply the derivative to our test function. So dv dx, and then integrate it over x. And now let's talk a little bit more about what the test function actually is. I mean, of course, there is a more serious mathematical definition here, but for the sake of our derivation here, we can think of the test function as something that is similar to our unknown function u. And recall, for the heat PDE, the unknown function was a temperature field, and the test function is a collection of all other admissible, or not other, but all admissible temperature fields. And what do I mean by admissible? Admissible means that they also have to adhere to the boundary conditions. So here we drawn the hypothetical analytic solution and also the piecewise approximation as we expected in the finite element method. And you can think of a test function as a function which can look whatever you like. So for instance, maybe something that looks like this, really crazy, but the big point is that it also adheres to our homogeneous boundary condition. I will just quickly remove the function here, but I think you get the point. So everything that also adheres to the boundary condition, but can have arbitrary shapes in between. I mean, of course, there are some restrictions, but at least that's a way to think about that. Okay, and the big point now is if those functions v adhere to the boundary condition, then of course the boundary evaluation of them will be 0. And then if we multiply them with something, so 0 multiplied with something will just give 0, and therefore this boundary evaluation term will be 0. Okay, let's note that down. So this one will be 0, and that is because the test function has to comply with the boundary condition of u, so which was our original unknown. So in other words, it has to be 0 on the boundary. So it is 0 on the boundary, because in our case, we have homogeneous Dirichlet boundary conditions. And then this entire term will just cancel out, and we basically keep the left-hand side and then the integral with the minus sign in front. So we have the integral from 0 to 1 over du by dt times v dx is equal to minus the integral from 0 to 1 over alpha du dx and then dv dx integrated over x. And this is now the weak form that we need in order to translate our problem to FEniCS. Maybe let me quickly highlight that this is a v here, not a u. And essentially it keeps the characteristics of our heat PDE, but now our solution function u is only required to be 1 times continuously differentiable. If that does not say much to you, don't worry, it's just a technicality. It's a way in order to describe our PDE problem to FEniCS. By the way, we can also equivalently write this in Residuum form. So let's put this into Residuum form. And in that particular case, we will just have a 0 on one side. So we will have the integral from 0 to 1 over du by dt times v dx plus alpha du dx dv dx integrated by dx, or maybe I want to put it into one big integral, and then this one shall be equal to 0. And now you can think of FEniCS as a way in order to discretize spatial derivatives for us. So FEniCS is going to take over the discretization using those finite elements. But this still leaves the discretization in time left for us. So we still have a continuous derivative in time. And we can get rid of this by applying an Euler step, or just discretizing our time using an Euler step and introducing u's at 2 different time levels. So we will introduce a u at time t plus 1, so at the next time step, and u at time t. So this is a value that we know from a previous iteration in our time-stepping procedure, and for the 0th iteration in that procedure, we know it from the initial condition, and then we have a t plus 1, which is the value in a subsequent iteration. So by doing so, we will discretize our Residuum form and get the integral from 0 to 1 of u at t plus 1 minus u at t divided by delta t, which is our time discretization, multiplied with v, and then plus alpha du dx, but wait a minute, du, so we have to discretize u. And now we have to select from which time step we are choosing u for this spatial derivative here. And there are 2 options. I mean, we could use it from the previous step in time or from the next step in time. And if we choose it from the previous step in time, we will get an explicit discretization, and if we choose it from the next step in time, we get an implicit discretization. And here I want to choose an implicit discretization in order to not have a restriction on the time step. So we will choose it also from the next step in time, multiplied with the derivative of v with respect to x, and then dx is equal to 0. And this v here does not require a time step or a time step index to say. And now you kind of have to think of that as before our primary unknown was u, and now our primary unknown is u at t plus 1. So this will now be our primary unknown. So this is the primary unknown here, because we want to solve a finite element problem in order to advance in time iteratively. And the u at time step t is not an unknown because we know it from the previous iteration in time. The v, I mean, it's not an unknown, it's just an technicality in order to prescribe a weak form. And alpha is also known, and we choose the delta t to our liking. Let's just rearrange this equation a little bit by multiplying with delta t. And then we get the integral from 0 to 1 of u at time step t plus 1 multiplied with v minus u at time step t multiplied with v plus alpha times delta t multiplied with the derivative of u at t plus 1 with respect to x multiplied with the derivative of v with respect to x multiplied or integrated over the x is equal to 0. And now that's our weak form, at least in this one-dimensional case. However, FEniCS does not accept it that way because it is built more generally for multi-dimensional cases where u depends on more than just one spatial coordinate. Because of that, we have to derive the weak form in this more general multi-dimensional case. But don't worry, we will do that together. It has one point where it's going to be a little bit more complicated, but I'm going to explain that. Okay, so what we're going to do now is to do all these steps we've done in the one-dimensional case, again, in the higher dimensional case. Derive weak form in higher dimensional case. X, so our spatial dependency, is now from a d-dimensional space where d is greater or equal to 2. I mean, in the end, we will still stay one-dimensional, but the result we're getting out of these derivations is the weak form that FEniCS accepts. For this, we have to use the strong form in the multivariate case, or in this higher dimensional case. And this one is reading as du by dt is alpha times nabla squared u. And this nabla square you see here, this is essentially a different way of writing the Laplace operator. So this is the Laplace operator. And for instance, let's do a two-dimensional case. Then this would read, so in 2D, you would have du by dt is alpha times second derivative of u with respect to x plus second derivative of u with respect to y. So this is just a handy collection of second derivatives. If we had a third dimension, it would be the second derivative with respect to z, and so on and so forth. But the steps, as said, they will stay the same. So first step again was to multiply with a test function. Okay, let's do that. So let's keep our multi-dimensional heat equation and multiply with a test function. So du by dt multiplied with v is equal to alpha nabla squared, or Laplace operator, applied to u multiplied with v. Then second step is to integrate over the domain. And here I just want to be more general and call this domain omega. I mean, in our one-dimensional case, we will keep having a one-dimensional domain, so the interval from 0 to 1, but this is just more general in order to also comply with this multi-dimensional scenario now. And so this will be the integration over a domain omega, and then this is over du by dt times v integrated over the volume. So this is a volume integral is equal to the integration over omega of alpha times the second derivative applied to u. And I'm putting this into brackets here because this second derivative is only applied to u, but not applied to v. So v is just multiplied with the result of the Laplace operator applied to u. And then here we will have a volume integral again. And now we have a third point, which will be a multi-dimensional integration by parts. Because recall again, the one-dimensional scenario required us to move one differential operator or one derivative from u to v. And you can think of nabla squared as the collection of second derivatives, and we want to move the one level of differentiation over to v. And for this we will make usage of the so-called Gauss or divergence theorem, which allows us to perform multidimensional integration by parts, among other things. And for this I have to answer the question, like, how can we perform integration by parts with a Laplace operator? This is, I mean, when I heard that the first time, this was extremely confusing to me. So let me try my very best to explain that. Let's again keep the integral over omega of alpha nabla squared u times v dv, and this is, well, question mark. And the trick here is to write the Laplace operator as the divergence of the gradient. So this was nabla squared, and recall this was nothing else than the Laplace operator. So people use different ways of writing that. And this is equal to the divergence of the gradient. So if we take the nabla operator and dot it with the gradient operator, we get our Laplace operator, or in other notation, you could also write the diff of the gradient of something is equal to the Laplace operator. So in other words, we could say that we have the divergence of the gradient of u multiplied with v, right? So this is kind of our first result here, but now we have to make usage of a reverse product rule. Okay, crazy again, don't worry, we will go over this. So now we will use the reverse product rule, and for this we will come up with a quantity to which we apply the product rule, and then we are going to identify this one such that we can find an equal expression for this. Okay, for this, imagine we had the following expression, which was the divergence of the gradient of u multiplied with v. So the gradient of u turns our scalar value temperature field into a vector field. And if we multiply a vector field with a scalar field, this is element-wise multiplication, this still gives us a vector field. And then if we take the divergence of that, we again get a scalar field. And let's apply this divergence by the help of the product rule. So in essence, this one is equal to, well, we first have the divergence applied to this one. So divergence of gradient of u multiplied with v plus, and then we apply the divergence to v. Well, what is the divergence of a scalar field? Yeah, it is the gradient in that sense. But in order to still get a scalar, we have to use the dot product between two gradients. So we have gradient of u, dot product, gradient of v. Okay, once again, this is just a product rule. We apply a differentiable operator. So maybe to give you an example in 1D, so in one dimension, you might have d by dx applied to du by dx multiplied with v. And then you would get, well, first, second u with respect to x times v plus du by dv times dv by dx. So, sorry, my v and my u, they are hard to distinguish. I hope this was not confusing. So again, this is just a multivariate analogy of that. And why I did that is because here we can now identify our Laplace on u multiplied with v. So we can write that the Laplace on u, so Laplace on u times v, is equal to this one minus this one. So first, the divergence of the gradient of u multiplied with v minus the gradient of u dot product with gradient of v, of course. Sorry, so this is v here. Okay, why did we do that? Because now we can replace this term in our integral with this one here. So finally, we will get, so we keep the integral over omega with du by dt times v d volume is equal to the integral over omega. And then we actually just had that one, of course, multiplied with alpha up front. But now let's replace it with what we had here. So we had first the divergence of the gradient of u multiplied with v volume integral, and then minus omega alpha gradient u by gradient v dot product, of course, integrated over the volume. Now we have two integrals, so why did we do that? So now because we can apply the divergence theorem here. So this one is the divergence of a vector field integrated over a domain. Well, that calls for the divergence theorem. So this one calls for the divergence theorem. If that doesn't say much to you, no worries. This is just a trick for us in order to identify that this integral will vanish. In essence, our right-hand side transforms. So we keep the second integral, which was the integral over omega of alpha and then gradient u dotted with gradient v integrated over the volume. And here we will get a surface integral over d omega, and then we keep our alpha, and now we will have the normal unit vector, outward facing normal unit vector, multiplied with this expression here, gradient u times v, and then integrated over the surface. Now we again recall v, that was a test function. So it could be anything within the domain. So I mean, not anything, but I think of it as anything, but it has to adhere to the boundary conditions. And on the domain boundary, where we're doing an integral over, our v is 0. And therefore, the entire surface integral will be 0. So again, let me highlight this here. The test function is 0 on the domain boundary. And therefore, this entire integral will be 0, so it vanishes, in other words. And we keep this one. And isn't that cool that this right integral looks somehow close to what we found in 1 dimensions? So in 1 dimensions, where was it again? So here, yeah, here is it. There we had an integral, so I mean here we moved it already to the left-hand side. Maybe let's use this one here. And here we had first derivative of u with respect to x times first derivative of v with respect to x. And now we have gradient of u dotted with gradient of v. And this is just a multivariate or multidimensional analogy to this. Isn't that cool? So, I mean, of course it was more technical, but in the end we found the same characteristic, because the heat PDE, let it be in 1 dimension, 2 dimension, 3 dimension, whatever dimension you want, kind of has this characteristics that its weak form will always give this kind of structure. Okay, long story short, now we have the weak form in multidimensional case. So finally we will be having first integral over omega of du by dt times v integrated over the volume is equal to the negative integral over omega times alpha gradient u dotted with gradient v d volume. Okay, next step, let's move it again into the residuum form. So let's have the residuum form, which is du by dt times v plus alpha gradient u dotted with gradient v over the volume shall be 0. And then we will again do the temporal discretization, similar to what we've done before. So we will get integral over omega of u at t plus 1 minus u at t divided by delta t times v plus alpha times the gradient of u. And now we can choose again whether we want from the previous step in time or the next step in time, but I would want to have at t plus 1. And then we dot that one with gradient v dv is equal to 0. And let's just have some final rearrangements by multiplying with delta t. And then we get our weak form. Let me put it in yellow here, which, or this is the form we're going to use in FEniCS. So we will have u at t plus 1 times v dv minus the integral over omega u at t times v integrated over the volume plus the integral over omega delta t times alpha, and then gradient of u at next time step dotted with the gradient of v, and integrated over the volume. Here we go, final weak form. That was a long derivation, but I hope it gave some insights in how you could take almost any PDE and transform it into its weak form. Of course, given you know these smaller tricks, but often there are only some certain structures of PDEs that you want to solve with FEniCS. Okay, let's translate what we just derived into the FEniCS code in Python. For this, I again have our weak form over here. And now before we can translate that, we first have to define the test function. And we're also going to define the trial function. The trial function is going to be a representative for the primary unknown in our weak formulation. So let me say this here. First, we are going to create the weak form. For this, let's define the u trial function. So this will be the representative of u at the next point in time. For this, we will use FEniCS.trial function. And then as with every function here, we have to select a function space. And I want to again use, maybe let me move that a little bit up here. and then I again want to use a Lagrange space, and then we can create a vtest function by saying FEniCS.test function on this Lagrange polynomial space. Okay, then let's create the weak form Residuum, because I want to work in terms of this Residuum form, and I will just get an opening and closing brackets in order to move that into more than one line. And the first step is going to be utrial multiplied with vtest integrated over the volume. And in order to represent an integral, we only need the differential at the end for FEniCS by saying fe.dx. And dx can be understood as the volume integral we have here over the domain omega, which is also represented by the help of the mesh that we use, because the mesh then also represents our domain. Next step is this one here, so minus, and then we have u old, so the solution from the previous step in time. And recall, we set that to be the initial condition, but later on in the time loop, we will override this solution such that it's always the solution from the previous step in time, multiplied with vtest, and then also integrated over the volume. And then the last step, which is this one here. For this, we of course first have to define a time step length, and I want to set this one to 0.1. And then of course we also need a diffusivity. So I will use a diffusivity of 1.0, and then we will be having time step length multiplied with diffusivity multiplied with, well, now we have to represent our gradient. So let's just do fe.gradient on the solution at the next point in time, which was our trial function. And then we have dot product. Well, how can we do the dot product? Well, of course, FEniCS also has something for us. So we have fe dot, and this takes two arguments. First, the gradient of u trial, and then we will have fe.grad on vtest. Here we go. Is it? Yeah, that's it. And then integrate over the domain again. So multiply with fe.dx. Delete the next line, and that's our weak form. Since we have a linear PDE, this weak form Residuum is separable into a left-hand side and to a right-hand side. So say weak form left-hand side, and we can extract the left-hand side from the Residuum by saying fe.left-hand side on the weak form Residuum. The left-hand side will be all the terms which contain our primary unknown. So these are the last integral as well as the first integral, because those have u at t+1. And the right-hand side, so weak form right-hand side, is going to be this one here, which contains the solution from the previous step in time. So here we go. And that's already it we need in order to start our time loop. So let's do our iteration by saying for t in range of maybe 5 steps. And there we first have to advance our solution by solving the finite element problem. So we can use the convenience routine FEniCS.solve and then apply it to our system of equations, which is going to be weak form left-hand side equals weak form right-hand side. And FEniCS is using an overloading of the equality operator. And for this, we also have to provide FEniCS with a way in order to store its solution. And for this, FEniCS is using its own kind of format to represent these fields. So far, we have this trial, but trial is more of an abstract concept than an actual field in which we can solve or store a solution. And for this, we have to create this solution field. So u solution is going to be fe.function on our function space. And then we can say, well, solve the finite element problem and store it in u solution while adhering to the boundary conditions. Boundary condition. our homogeneous Dirichlet boundary condition. So FEniCS, what is FEniCS going to do? So FEniCS is going to apply all the machinery of finite elements, which means that it is subdividing our domain according to the finite elements we created by the help of our mesh. Then in each finite element, it is going to evaluate the integrals and build up a linear system of equations for the degrees of freedom that are unknown to our solution. And then it also prescribes the homogeneous Dirichlet boundary condition for us. And finally solves this linear system of equations using a linear solver. And all of this kind of in the background. So we will just get our solution out. And then of course we can plot the solution by saying FEniCS.plot u solution, which will plot the solution in a matplotlib window. Finally, of course, in order to iterate in time, we have to set the old solution to the new solution. And we can just do this by saying uold.assign u solution. Or not, maybe there's a typo, so it should be assigned. So let me move over the weak form again, and then let's just finish off with some small modification to the plot. So I first want to have a label in here with the corresponding time that we're currently at. So let's have a time current, which starts at 0. We'll just do time current plus equal time step length. And then we can use FEplot with a label keyword argument and use a formatted string and saying time equals time current. And then let's format it as a floating point number with 1 digit after the comma. Finally, let's make a legend appear and then show the plot, because this is plotting all the solutions into one matplotlib figure. And then let's try and run this code. Python heat conduction simple, and hopefully this will work. So we see FEniCS is doing something here, and finally here we go. Beautiful. So we see that the FEniCS compiler is running, it's creating this finite element problem, and then it can solve it. So here it says solving linear variational problem, and here we see our solution curves at certain points in time. And as proposed in the beginning, we have our qualitative behavior, which kind of remains. It will just get smaller. So our magnitude decreases because our energy, our temperature is flowing out over the boundaries. That's the end of this video. I hope you enjoyed it and it gave you more insight into how FEniCS works and how to derive those magical weak forms that you need for finite element problems. You will find the source code as well as the PDF with the derivations linked down in the video description. A big thanks to all the Patreons of the channel. If you also want to support my vision of free education on these advanced mathematical topics, you find the link to the Patreon page down in the video description. If you enjoyed this video, then I would be happy if you consider subscribing to the channel. There's more awesome content like this and also more FEniCS tutorials. Feel free to give the video a thumbs up if it helped you. Thank you so much for watching. Here you will now see similar videos, and I hope to see you in one of the next videos.